torque motor is a type of electric motor that directly produces torque, which is rotational force, without needing gear reduction. Unlike conventional motors that convert electrical energy into rotational motion, a torque motor provides direct torque output, making it suitable for applications that demand precise rotation control. An alternating current adjustable voltage motor, often abbreviated as a CAV motor, is an alternating current motor that features variable voltage control. By adjusting the voltage applied to the motor, the speed and torque of the motor can be regulated without a mechanical transmission system. CAV motors find applications in various areas, such as fans, pumps, and industrial machinery, where precise speed control is important. Torque motors and traction motors are both types of electric motors. However, their specific applications differ. Torque motors are used in applications that need precise torque control, such as robotic arms, medical devices, and computer numerical control, also known as CNC machines. Traction motors are used in applications that need high torque and speed, such as electric vehicles, locomotives, and conveyor systems. While both torque motors and traction motors are used in various industrial and automotive applications, they are designed for different purposes. Torque motors prioritize precise torque control, while traction motors focus on delivering high torque and speed. Considering motor protection, several factors are critical for ensuring the longevity and reliable operation of electric motors. Firstly, overload protection is essential. Overloads occur when a motor draws more current than its rated capacity, typically due to excessive load or mechanical issues. Overload relays or electronic motor protection devices are used to detect overcurrent conditions and trip the circuit, preventing motor damage from overheating. Secondly, short-circuit protection is vital to protect against severe fault currents that can arise from insulation failures or wiring faults. Fuses or circuit breakers with appropriate interrupting ratings are installed to quickly disconnect the motor from the power supply in the event of a short circuit, minimizing equipment damage and safety hazards. Thirdly, undervoltage protection is needed to prevent motors from operating under low voltage conditions, which can cause reduced torque, increased current draw, and potential overheating. Undervoltage relays monitor the supply voltage and trip the motor circuit if the voltage falls below a predetermined threshold, protecting the motor from damage. Fourthly, phase loss protection is important for three-phase motors, as the loss of one phase can lead to unbalanced currents, overheating, and potential motor failure. Phase loss relays detect the absence of a phase and trip the motor circuit, preventing damage. Fifthly, ground fault protection is crucial to detect insulation failures that cause current to flow to ground. Ground fault circuit interrupters, also known as GFCIs, or ground fault relays, are used to monitor the ground current and trip the circuit if a ground fault is detected, reducing the risk of electric shock and equipment damage. Sixthly, temperature monitoring is sometimes employed, especially for large or critical motors, to directly monitor the motor winding temperature. Resistance temperature detectors, also known as RTD or thermistors, are embedded in the motor windings to provide temperature feedback to a protection relay, which can trip the motor if the temperature exceeds safe limits. Seventhly, proper ventilation and cooling are important to dissipate heat generated by the motor during operation. Regular cleaning of motor cooling fins and ensuring adequate airflow can prevent overheating and extend motor life. Eighthly, surge protection can protect motors from voltage spikes caused by lightning strikes or switching transients. Surge protective devices, also known as SPD, are installed to divert surge currents away from the motor, preventing insulation breakdown and equipment damage. Finally, regular maintenance and inspection are key to identifying and addressing potential problems before they lead to motor failure. This includes checking for loose connections, inspecting insulation, lubricating bearings, and performing insulation resistance tests. Proper motor protection requires a coordinated approach that considers all of these factors. The selection and coordination of protective devices must be based on the motor's characteristics, the application requirements, and applicable electrical codes and standards, such as those outlined by the National Electrical Code, known as NEC, and the Institute of Electrical and Electronics Engineers, known as IEE. The NEC, specifically Article 430, provides detailed requirements for motor circuits and protection. Understanding and adhering to these requirements is essential for ensuring the safe and reliable operation of electric motors. For example, NEC Section 430.52 addresses motor short circuit and ground fault protection, specifying the maximum allowable ratings for fuses and circuit breakers based on the motor's full load current rating. Section 430.32 covers motor overload protection, requiring overload devices to trip at a specified percentage of the motor's full load current. Section 430.6 provides guidance on determining the motor's full load current for various calculations, emphasizing the importance of using the values listed in NEC tables rather than the motor nameplate current in certain cases. Motor control circuits are vital for operating and controlling electric motors in various applications. These circuits consist of components that initiate, stop, regulate, and protect motors, ensuring efficient and safe operation. Firstly, starters are essential components used to start and stop motors. They range from simple manual starters to sophisticated electronic starters. Manual starters are basic switches that directly connect the motor to the power supply. Magnetic starters use electromagnetic contactors to control the motor, providing overload protection and remote operation capabilities. Solid-state starters use electronic components to gradually increase the voltage applied to the motor during startup, reducing inrush current and mechanical stress. Secondly, push buttons and selector switches are common control devices used to initiate or change the operation of a motor. Push buttons are momentary switches that activate a function when pressed, such as starting or stopping the motor. Selector switches offer multiple positions to select different operating modes, such as forward, reverse, or jog. Thirdly, relays are electromagnetic switches that control a circuit by opening or closing contacts in response to a control signal. They are used to implement logic functions, interlocking, and sequencing in motor control circuits. Overload relays protect motors from excessive current draw by tripping the circuit when an overload condition is detected. Time delay relays introduce a time delay before a circuit is activated or deactivated, allowing for sequential operations and preventing simultaneous switching. Fourthly, control transformers provide a reduced voltage power supply for the control circuit, typically 120 volts or 24 volts, ensuring safer operation and compatibility with control devices. They isolate the control circuit from the main power supply, reducing the risk of electric shock. Fifthly, pilot devices such as indicating lights and meters provide visual feedback on the status of the motor and the control circuit. Indicating lights show whether the motor is running, stopped, or in a fault condition. Meters display parameters such as voltage, current, and speed, allowing for monitoring and troubleshooting. Sixthly, programmable logic controllers, also known as PLC, are advanced control systems that use programmable logic to control motor operation. They offer flexibility, scalability, and advanced control capabilities, such as PID control, sequencing, and communication with other devices. PLC can be programmed to implement complex control algorithms and integrate with supervisory control and data acquisition, known as SCADA systems. Seventhly, variable frequency drives, also known as VFD, are electronic devices that control the speed of alternating current motors by varying the frequency and voltage supplied to the motor. They offer precise speed control, energy savings, and soft starting capabilities. VFD are used in applications such as pumps, fans, and conveyors, where variable speed operation is required. Eighthly, motor protection devices such as circuit breakers, fuses, and overload relays protect motors from electrical faults and overloads. Circuit breakers and fuses provide short-circuit protection, quickly disconnecting the motor from the power supply in the event of a fault. Overload relays protect against excessive current draw that can cause motor overheating and damage. Ninthly, wiring and conduit provide the electrical connections between the control components and the motor. Proper wiring practices, including the use of appropriately sized conductors, secure connections, and proper grounding, are essential for ensuring safe and reliable operation. Conduit protects the wiring from physical damage and environmental factors. The design and implementation of motor control circuits require careful consideration of the motor's characteristics, the application requirements, and applicable electrical codes and standards. Proper selection and coordination of control components are essential for ensuring efficient, safe, and reliable motor operation. The National Electrical Code, specifically Article 430, provides detailed requirements for motor control circuits, including wiring methods, overcurrent protection, and control circuit design. Understanding and adhering to these requirements is essential for ensuring compliance and safety. For example, NEC Section 430.71 covers motor control circuit conductors, specifying the allowable ampacity of control circuit conductors based on their insulation type and ambient temperature. Section 430.72 addresses motor control circuit overcurrent protection, requiring control circuits to be protected against overcurrent by fuses or circuit breakers. Section 430.74 covers motor control circuit disconnecting means, requiring a disconnecting means to be provided for the control circuit to allow for safe maintenance and troubleshooting. Alternating current motors are widely used in various industrial, commercial, and residential applications due to their reliability, efficiency, and versatility. Understanding the different types of alternating current motors and their characteristics is essential for selecting the right motor for a specific application. Firstly, induction motors are the most common type of alternating current motor, known for their simple design, rugged construction, and reliable performance. They operate on the principle of electromagnetic induction, where a rotating magnetic field in the stator induces current in the rotor, producing torque. Induction motors are available in various designs, including square cage and wound rotor types, each with different performance characteristics. Secondly, synchronous motors are alternating current motors that operate at the constant speed, synchronized with the frequency of the power supply. They have a rotor that is magnetized by either permanent magnets or direct current excitation, which locks into the rotating magnetic field produced by the stator. Synchronous motors are used in applications that require precise speed control, such as timing devices and generators. Thirdly, wound rotor motors are a type of induction motor that has a wound rotor with slip rings, allowing external resistance to be added to the rotor circuit. This allows for control of the motor's torque and speed characteristics, making them suitable for applications that require high starting torque or variable speed operation. Wound rotor motors are commonly used in cranes, hoists, and other heavy-duty applications. Fourthly, single-phase motors are alternating current motors that operate on a single-phase power supply, commonly used in residential and light commercial applications. They require a starting mechanism to initiate rotation, such as a capacitor start or split-phase design. Single-phase motors are used in appliances, fans, and small machinery. Fifthly, universal motors are alternating current motors that can operate on either alternating current or direct current power. They have a wound stator and rotor, with brushes that make contact with the commutator on the rotor. Universal motors are known for their high speed and high torque to size ratio, making them suitable for applications such as power tools and vacuum cleaners. Sixthly, servo motors are alternating current motors that provide precise control of position, velocity, and acceleration. They are typically used in closed-loop control systems, where feedback from sensors is used to adjust the motor's operation. Servo motors are used in robotics, CNC machines, and other precision motion control applications. Seventhly, stepper motors are alternating current motors that move in discrete steps, allowing for precise positioning and control. They have a rotor with multiple teeth or poles that align with the magnetic field produced by the stator windings. Stepper motors are used in printers, plotters, and other applications that require precise incremental motion. The selection of an alternating current motor depends on various factors, including the application requirements, the power supply available, and the desired performance characteristics. Considerations such as starting torque, speed range, efficiency, and environmental conditions should be taken into account when choosing a motor. Proper installation, maintenance, and protection are essential for ensuring the reliable operation and long lifespan of alternating current motors. Regular inspections, lubrication, and cleaning can prevent premature failure and maintain optimal performance.